This video is the first in a series about rapid control prototyping for electric motor. The objective of these videos is to show that the use of MATLAB Simulink and mplab device block for Simulink facilitates the implementation of real-time advanced control strategy for electric motors. I'm Romain Delpoux, I am Associate Professor at INSA de Lyon, and this work is joint work with Lubin Keruel, developing mplab device block for Simulink toolbox at Microchip. Here we present the first steps towards the implementation of a vector control law. Vector control is a sophisticated algorithm. On this figure we have the schematics of a permanent magnet synchronous motor. To spin this motor we need to apply three different voltages, and as output we have the position and or the velocity. The voltages are obtained thanks to an inverter, and this inverter is controlled by pulse width modulation. The pulse width modulation is a border between the digital signal controller and the physical system. Thus, the control algorithm purpose is to compute the duty cycle in order to apply the correct voltages to the permanent magnet synchronous motor. If we want a feedback controller like speed control, we need mechanical sensor and feedback the measured position and velocity to the control algorithm. To improve the control strategy, it is also required to measure the currents, and these current measurements need to be synchronized with the PWM in order to avoid measurement when we have commutation in the inverter. Finally, the control reference is also fit to the control algorithm. As we can see on this figure, we have different colors representing the sampling frequency of the signals. The control strategy is thus a multitask control strategy to be embedded in a microcontroller. Thus, the problematic is to know how to implement this sophisticated algorithm in an industrial microcontroller. For this purpose, we will use rapid control prototyping using mplab device block for Simulink and MATLAB. The strategy is based on the model-based design solutions, and the objective is to program a control law using Simulink and then generate the code and implement this Simulink code into the microcontroller. This is done thanks to mplab device block for Simulink, and when we click on the build button on Simulink, the solution implements a scheduler, compiles the generated code, and programs the chip directly. Let's move to the demonstration. So, on my screen, we have the Simulink model. In the middle, we have a template that can be downloaded directly from the mplab device block for Simulink toolbox. We have built it around all the different blocks in order to perform the control. We have the modulation for the PWM, the part transformation and the inverse part transformation, and the control. The video will be dedicated to the detail on the different blocks present on this Simulink model. The proposed control algorithm can be used with a different switch on the board. We have the switch 1 to enable or disable the control, the switch 2 for the mode. We have an open loop mode that will apply different voltages to the motor using the potentiometer, and we have a speed control using the switch 2 mode. The switch 3 will reverse direction of the motor. So, as a hardware, I have two different LVMC board, one for the Technic motor and one for the Earth motor. In order to evaluate the performance of the control algorithm, I will use the PIGI that is provided by the mplab device block solution. A video will also be dedicated to this PIGI. So, if I connect my serial link, I can start an algorithm that can be downloaded with the solution. On this screen, we can see that I plot the VDQ voltages of the motor, the IDQ currents, the speed and the speed reference. The first mode is open loop. I can visualize here the DC voltage applied to the board and the maximum voltage that the phases can apply to the motor. And here we have the CPU load. So if I press on the switch 1, I will enable the control. And then if I change the potentiometer, I can modify the voltage applied to the control. Now if I press on switch 2, I will change to the speed control. So here on the figure we have the reference and the speed measurement, and we can see that if I change my potentiometer, we can see that after a small transient, the reference speed is perfectly tracked. If I press on the reverse direction, I will change the direction of my motor. Here we can see that the entire vector control strategy takes only 46% of the CPU load. Now, if I want to apply the same control strategy to the other motor, I simply need to open this block, motor parameters and gain tuning, and choose another predefined motor. So if I want to choose a long burst, you will see that the pole pairs and the motor parameter will change when I click on apply. I pass this from 4 pole pairs to 5 pole pairs, and different parameters have changed. Again, with this motor, I can generate the code and flash my program into the chip, build the model, select a programmer, and flash the code. In the same manner as the previous motor, I can enable the control and apply open loop control, speed control, and reverse the direction of my motor. This demonstration ends the video about getting started to vector control. At the end of the slides, you have different technical appendix in order to apply this control at home. We hope that you enjoyed this video, and we thank you for your attention.